Hello and welcome to a rabbit hole. Here we're going to be talking about modeling simple air resistance. We're going to design ourselves a formula for air resistance, create a new air drag component, and then test the flight against Unity's reference ball so that we get similar results to Unity's physics engine. So let's take a look over at Wikipedia. I'm telling you, it's a rabbit hole. It's going to be fun. So how do you calculate the drag on an object moving through a fluid? Well, firstly, let's say we don't have a fluid in our simulation. And I'm going to let that go for now. So Newton's third law says that every force has an equal and opposite force. You should be saying right now, hold on, if there's a drag on this ball, how come, what's creating that drag? Good question. We're not actually going to put a block of air in yet. I may extend the course to include the effect of the ball or the object on the air later, but we should do that after we've talked about collisions and the mechanics of collisions, really. So let's talk about drag for a minute. If you get to the Stokes flow page on Wikipedia like this, this is when an object's moving very slowly and the streamlines behind it are basically end up the same as in front of it. Then there's been no net change of momentum on the air. So all of the drag is just in this middle region where the skin friction with the sides of the ball. All right, so if you scroll through all the maths in here, then eventually, don't read it all, and please don't get too scared unless you are actually a mathematician. But somewhere down here, I've managed to decipher the bit that matters. Let me just find the equation. Here we go. Theorems about Stokes' law, Stokes drag. Here is a formula that says the drag is proportional to the velocity, basically. All of these other things, the pi, the mu, the a, are effectively constants. So this is suggesting, that the force, the drag force, is proportional to velocity. Velocity, normally v, it's u in this case, to the power of 1 when it's very, very slow. Now let's move up a level to the drag brackets physics article, and it then elucidates and says, well, hang on, this is all very well at very, very, very low flow speeds where it's all skin friction, as I said, and no what we call form drag. But as soon as you go to more realistic shapes and more realistic speeds, you start to get form drag. This is an aerofoil with low form drag, which is good. You want as little form drag as you can have. And then as you go up, your form drag increases. Now, what the hell's this form drag? Form drag is basically a result of mucking up the momentum of the air. Their air was steaming in from the left relative to the object, and when you finished hitting it with a big fat ball, it's now stationary and disorganized and spinning round in circles. And that's what's caused the form drag, right? You're basically hitting the air and causing a massive change in momentum. Of course, it's even worse if you have a flat plate. So the question comes, what happens as the speed starts to increase? Well, as soon as we break out of normal drag, we go to this type of equation, where, again, it looks like lots of units, but half is a constant, rho, the density of the fluid, is a constant, v squared now. So remember the previous Stokes law said to the power of u, or v, just interchange the letters, to the power of 1. This is to the power of 2. Then we have a coefficient of drag and then an area. We're not worrying about the area because we're dealing with a point object at the moment. But the coefficient of drag also changes slightly with speed. Look at this curve over here. You can reason this through in your own time, but just notice that the coefficient of drag drops as the Reynolds number increases, and the Reynolds number tends to increase with velocity. So, what the hell does all that mean? That basically means, again, that if the Reynolds number is very, very low, then the coefficient of drag will be higher than you'd expect. So we wouldn't quite have an effect of v squared. It would be a lower effect. Look, we could keep going down this damn rabbit hole. I vaguely know what I'm talking about at this point. You're probably confused to hell. If we start introducing things like non-Newtonian fluids, cornstarch, these type of things, where the viscosity doesn't even change linearly with the strain on the fluid, then your head will start to explode, and it'll certainly have exploded by the time we get to the Navier-Stokes equations, which look beautiful and compact, and are actually very elegant, but we're not prepared yet to start solving these in our engine because you're going to need to know about del operators, dot products, partial differentials, and a bunch of other stuff we don't need to cover yet. So, what's my solution? How the hell are we going to get a simple drag equation? Well, look, in practically all cases that we've talked about, it's simply some constant times the velocity to the power of something between 1 and 2. Some constant times the velocity to the power of 1 or 2. Let's just get on with it. It's going to be really simple using that paradigm. So, where are we? Calculate gravity. Well, do we want to be using the same thing, the same physics engine, or do we want to create a new component for air drag? I want to create a new component. Air drag is optional. So I have a rigid body hanging around here I'm going to remove. I'm going to add a component and call the script air drag, or what did we say in our challenge slide? I think we said fluid drag. Over here I've called it fluid drag. Let's be more general and say fluid drag. So create yourself a script called fluid drag. And attach it to your ball. Perfect. Let's go into that fluid drag script once we've tidily organized it into our scripts folder. And let's quickly get this maths written down. So what do we need? What do we need in terms of public constants? Well, firstly, I want something with a range of 0 to 1, which is going to be a public float drag exponent, let's call it. It's v to the power of what? And it's not 0 to 1, is it? We said it was 1 to 2. So at very low speeds, the drag may be proportional to the velocity to the power of 1, as in Stokes' equation here, uv to the power of 1. And at higher velocities, v starts to approach the power of 2. So over in this equation here, we're going a load of stuff, but we're proportional to velocity to the power of 2. So, drag exponent or velocity exponent. Let's call it velocity exponent. Great. So that's going to be allowed to vary between 1 and 2. What's the other constant we're going to need here? Let's just call it drag constant. Right. What is the unit of velocity exponent? Well, it's just an exponent number that we're raising to, so it has none. And what are the units of the drag constant? I actually don't know yet. We'll worry about that in a minute. So let's create a method for calculating the drag now. Let's go void, pure object orientated, and then let's just say calculate drag, like this, and let's take in just the velocity as a float. Not the direction we'll worry about outside of this. Okay, so how do we calculate the drag? Well, in general terms, it's this constant we talked about times v to the power of the exponent. So you go ahead and write calculate drag now. It's just going to be the drag constant times v, the current velocity that we've passed in, to the power of the velocity exponent. Here's your challenge. Remember mathf.pow, and just write that small function for me now. Okay, welcome back. So it should be relatively simple. What we're going to say is return, and we will return a float, drag constant times mathf.pow velocity to the power of what? The velocity exponent. Okay, let's build, make sure that everything works, looks okay. Fantastic. Okay, so now what we need to do is attach our fluid drag component into our other physics engine. So we need these two lines. We need to get the component there, and we need a physics engine at the top. So I may as well just grab all of this stuff and then chop out what I need. So going to need to do this at the top of all of your components. We don't need this thrust. We're going to have a private physics engine, and then at the top here we are going to find the physics engine like that. That's great. Okay, fantastic. So in calculate drag, when are we going to calculate drag? Every frame, right? So void every fixed update. So fixed update. What are we going to do in fixed update? We need to do a few things. This calculate drag is great, but it just returns us a float. It doesn't know anything about the direction. And of course, drag is going to operate in exactly the opposite direction to the way that the thing is going. So where is it going? Well, it's going in a vector 3 direction, I presume. And it's called direction vector. And it is equal to physics engine dot, and then we need to look inside the physics engine and see what the property is. Velocity vector. Okay, that's fine. So we can call it direction vector or velocity vector. Let's call it velocity vector. So we have the velocity vector. We know how fast this thing's traveling. From that, we can get the velocity. What is the velocity? Well, it's a float. Velocity. Now, velocity is not really the right word, it's speed, because velocity includes a direction, so let's call it speed here, and rename everything to speed. What is the speed in terms of the velocity vector? It's velocity vector dot magnitude, right? Okay, so we have the speed to part in, so we're nearly ready to just physics engine dot add force, calculate drag, speed. But that's not a direction. Yeah, so calculate drag speed is just a magnitude. So let's go for float drag size equals calculate drag on the speed. Okay, and then we want a vector 3 drag vector equals drag size times velocity vector dot normalized, okay, which is the direction of it, but we want that in to be minus in the opposite direction. Okay, so then we literally just add this drag vector. Does that all make sense, the way I've broken that down for you? Let's try it. Let's see how this gets on. Let's see what sort of result we get with regards to the speed. Let's look at the ball. I'm going to make it default at 1.8, let's say. And I'm going to make the drag constant 1. Let's see what this does to the movement. Ah, it's better. It doesn't hit the goal now, right? So that makes sense. So that we can compare different balls in different parameters, just take a duplicate of the ball, make another one here called ball 2, and take the drag script off ball 2. So if you move this other ball a little bit in the Z direction, that will prevent the two balls from conflicting. The problem is the gravity force becomes massive when they're right on top of each other. We'll catch that exception if it ever comes up again. At the moment, just be aware of it. Move the balls apart, click play. And then if one of them has the air resistance on and the other doesn't, you get to see, especially if you pause, you get to see the behavior of the two balls in comparison. So you now got a drag component that's better than Unity's. If we look at Unity's very briefly, then all you have there is just a straight drag, which is close to your drag constant, right? But what it doesn't allow you to do with Unity is change this velocity exponent. You've got a lot more control than Unity had now over your drag. So you can change your curve in some nice ways. As a bit of homework, you may want to add a particle emitter to your ball at this stage so that you can see the tail it's leaving behind. But congratulations on getting this far. We have a really nice fluid drag component that is relatively simple in the way it works. Its only input is a velocity exponent and a drag constant. Another extra points homework for you is work out what the units of the drag constant must be. But don't stress if you can't do it. It's not so important right now. Well done, and I'll see you soon.